Approachable Haskell like DSL.
Right. Hey everyone, I'm Jasper. We had some technical trouble. Neither of our laptops works. I'm just going to use my text editor to show the source code of my presentation because Windows is the only operating system we tried that worked. Hi. So I work at Fugue. At Fugue, we build a cloud orchestration product. And imagine this the way, like a long time ago, people would manually install servers whenever they needed one. Fortunately, that has changed, and we arrived at a time where people would go through a web interface and click a few things, fire up a server that way. And now that's changing again, and going manually through a web interface gives you a lot of problems because it's not reproducible. You want to automate everything. So we see these products popping up which ease these things. And we are one of these companies doing this. We have our own DSL in which you can write your configuration, what you want your resources and your infrastructure to look like. And then you run our product and we enforce that. And you can find more info here. And it runs on AWS at the moment. How our DSL sort of fits into our general architecture is fairly simple. We have our DSL, which has a compiler. It outputs a specification. And then we ship that specification to a component called the conductor. This is a very high-level explanation. The conductor is a very complex piece of software. But for now, we can just regard it as a magical black box that does everything you want. And so this is sort of what using our software looks like. You write a file with the extension LW for Ludwig, which is what our DSL is called. You can also have multiple files, of course. Then you can run it. You give it sort of an alias so you can refer to the process later. You can edit it again and then update the running infrastructure, and you can kill it if you want. So let's dig deeper into the DSL, which is the part that this talk is about. So if you do, as I said before, like Fugue run, the Fugue tool calls our compiler, which compiles your specification down to something more low level. This DSL is mostly inspired by Haskell and OCaml, but also by simpler languages like YAML and JSON. And so it relates to Haskell in two ways. It's vastly inspired by Haskell, but the compiler for it is also written in Haskell. And first I'll go into the question a bit of why we're not just using YAML like so many other tools. YAML is sort of like the straightforward solution if you want a simple configuration format. Unfortunately, it has a lot of shortcomings. I think this quick example illustrates that very well. This is an example from Ansible. If you want to do a certain thing 3 times there, or you want to do a certain thing with a number of items, you quickly run into the problem that the language is really not composable. And we're used to neat and composable languages. And using something like this can be a bit of a pain at that point because, for example, we have the with items construct there, but then magically the name item is brought into scope, and it's not really clear what the rules are. Imagine when you want to have a nested loop or something. Do you use item 1 or an item 2? In fact, I don't know. So yeah, we want to have a more principled approach for a DSL like that. And here are some more problems with traditional configuration languages. There's no real standard way to document YAML files to sort of indicate what sort of possible strings can you put in at some point. Can you put a list there as well, or a number? With the traditional programming language, of course, you have a documentation generator. And especially for typed languages, if you run the documentation generator, it's very clear what sort of types you can put in which positions, right? Secondly, where do you store the configuration? And that's mostly about the defaults. Like if you don't specify a value, where does your program that reads the configuration, where does it store the default? Is it hard-coded in the program? Does it show up in the documentation? Do you have like a default configuration file? What if that goes missing? And the last item, which is also important, like if you just use a default YAML library, the error messages are often very unclear. You might just get a parse error at some line, or you might get a message like expecting a list here, but it's not really clear what the context is. So these are things that having a language more like a real language or a functional language with type system improves on. So that's why we decided to develop one of these. And these are sort of the design goals of our language. First of all, if you're doing a very simple task, it should be very simple. And we don't want the user to have more overhead than, say, YAML or JSON in these very simple cases. But secondly, if you want to do something advanced, for example, create a loop or have like some sort of abstraction of things you want to repeat, that should also be possible, and it should be possible in a clean way. You shouldn't have to sort of read files and splice in things. Basically, things should be composable. And also, the design goal, of course, we're not trying to build a new Haskell. Haskell can be a great motivation and like guiding language. It has many great ideas, but we're certainly not trying to build a general purpose programming language like Haskell. So let's start by giving a very simple example of a declaration in Ludwig, in our language. As you can see, it almost looks like YAML. You simply have a myVPC object with 2 keys, and both of them have value. One is the region in which you want your virtual private cloud, and the other one is a decider block. This looks like YAML, looks untyped, but in fact it's actually typed because we have a nice type inference. And this snippet is exactly the same, but we give an explicit type annotation here. So as you can see, Ludwig uses a structural type system for records, and it infers that region is a region because we know what this constructor is. This is a sum type, and we can figure out that cider is a string. And one of the clear advantages that almost immediately pops up is if I try to use USE3 there, for example, which doesn't exist, you immediately get a very clear error message. And this is already a huge improvement over what YAML would give you, unless, of course, if you would sort of manually have to add these errors to your configuration file format, but we get that for free. So let's go into the type system a little bit. So at first, we based our type system for this language on the scoped labels paper by Dan, and because this type system has very, very simple rules, which everyone likes, of course, but it's also very practical. It sort of extends Hindley-Miller with, I think, 3 rules, and you get a record type, which you can extend with new fields, and you can remove fields. But we quickly then ran into some shortcomings of that approach. This is sort of pseudocode that was using scoped labels. For example, we have this VPC type here, and because you have a structural type system, it's possible to add keys and remove keys as you please. For example, we might want to add like a tag to our VPC, and this is what it would look like using scoped labels, using some sort of made-up syntax. You could also do this with region, but at this point you have 2 region fields in here, and the type of myVPC changes, which is a bit confusing, and you can sort of get around that if you know Haskell very well and typed languages, but most of our users don't, so we don't want to do something like this here. This is what will be required in scoped labels, where you have basically another operator if you want to update a field rather than add a new field. And yeah, basically it's impossible to explain to people why this is a good idea, why you need another operator to override a field rather than extend a field. So one of the, I think, improvements, at least for our use case, we made is making extending a record the same as updating a record. So you simply override the fields that are there. And this required some more additions to the rules in the paper, and more precisely, we don't have field deletion anymore. But we still have principal types, which is a really nice property. And now we use a more simple syntax as well that is very easy to read for people who are familiar with languages like YAML and JSON. Like you can update, this sort of adds a new field to the record, and this sort of overrides the region field, and the other region field is thrown away. And these records turn out to be very, very useful for a configuration language, especially because pretty much everything is a record. So we have a lot of syntactic sugar for those things. For example, you can update fields deep within fields, or you can update fields through constructors, through some type constructors, a bit like Lens does, I suppose. And these sugars do very simple record updates. So the rules sort of stay very simple, but you can do very neat and complex things. So we have this cool language with lots of functionality for records. You can copy them, modify them. But it turns out that this is still not enough to build a really good configuration language. What's missing is sort of abstraction. And the AWS API, against which we work, and there's obvious connections between our libraries and the AWS API. A lot of use cases are very similar. For example, it's very, very common to have a load balancer, then some instances behind it. And we don't want people to sort of repeat themselves, right? Fortunately, there's this magical tool which enables code reuse in a very good way. And I'm sure you're all familiar with it. It's called functions. So this is a function call, and I'll explain later how exactly that works. But the cool thing is that using functions, we all know that you can build very, very complex abstractions and do cool things like remove repetition, of course. Like if you want to have multiple VPCs within the same region, we simply add a function, and you can call it twice, and that's all there is to it. We have some more syntactic sugar for function calls. As you can see, usually we use sort of like the traditional C-like way to call functions, not the Haskell style with a space, because that's a bit confusing for some of our users. But we have shorthands. Like in Python, you sometimes have these prefixes, for example, for Unicode, and it was very easy to extend our parser to also do this and do the same for records and lists. But it's still not enough, because if you sort of mirror the AWS API, you get a lot of functions like this. And it keeps on going here, and most of the things are optional. Optional is the Ludwig version of Haskell's maybe, so very simple. And it's correct, but it's not very nice to read code like this. And if you want to change one parameter, you have to find out the position and so on. So it's very clear that we want something like named parameters here. Having named parameters would allow us to do something like this, which is already a lot better. Unfortunately, it's not that easy to add named parameters to a Lambda calculus-based language. So how do we do this? Well, there's a very simple way. We can just use records for that. The function just takes a single argument, which is a record. And since we have the function call shorthand, it also looks relatively nice. We don't need to add the parentheses around it anymore. But it's still not very good. Because we have all the nonce here, and there's this weird thing with the optional going on here. Many people might wonder what I mean if they first have a look at the language. One sort of thing that's nice and you get for free when you use records as named arguments is that you can do tons of cool stuff because arguments suddenly become first class. You can sort of take all the arguments, modify them a bit, and pass them through another function really easily because it's just a record. And it's still type checked. You don't lose type inference. So let's talk quickly a bit about how we can improve this. All the nonce in here, not very nice to read, but unfortunately we need them to satisfy the type checker. While we really want to write this. So we added support for writing this in a reasonably nice way. We have sort of syntax-based coercions. So at some points in the syntax tree, we allow inserting coercions. And one of them is if you have a function call, then the arguments of the function are allowed to have non-padding. And this adds a special sort of a hint to the type inference engine. And when you see the constraint, you sort of so the type checker generates this constraint. And then when you get to the solver, it can solve this constraint. It sees that some things are missing, but it also sees that the missing things are optionals. So it just pads it with nonce for the missing keys. The second problem we had to solve there is this problem. It's very hard to explain to someone who has only had experience with Python or Bash or languages like this why this optional call is necessary here. It's very weird. I mean, they can see it's an optional parameter from the API, but why do we need to specify this? So we have a similar way to solve that. In our syntax-based coercions, if you have basically a record and you have something on the right side of a record key, we also add this special hint. And when it gets to the solver, it knows it can convert A to optional A. And of course, not the other way around. You can't convert optional A to A, of course. Yeah, so in conclusion, there's some advantages and disadvantages to these approaches. We think it's generally worth it. We give the optional type a bit of special treatment in the compiler, but it's very, very isolated. It's only in 2 or 3 places in the compiler, and some extra cases in the interpreter. The only downside is that we lose principal types, although you could always turn it on or off for a module if you wanted to. So I hope this was interesting. There's a special thanks to WellType because they helped us with some advice around all these things. And now there's time for questions.
Hello. Let me see. So in some cases you had, for example, a CRDR, like an address, and that was represented as a string or what have you.
Yes.
But say you do want to actually have, say you want to make sure they got it right or whatever. Say like put it a string and it gets all the way through, and then a runtime error, I can only assume, or something else. So if you were to represent like those addresses as something specific, then how would you go about, say, having something that can pass these addresses and then rejecting and error messages, and like how do you restrict things even further than what you got just in terms of beyond like just straight strings?
Yeah, so the question was if there's a better way to deal with string-based type, for example, the CIDR block, and we have that. So we don't have the So we could do something like this, where cider is a smart constructor, as we would call it in Haskell, which validates the string before actually generating the data type. We have that. We don't actually use the cider thing here, but what we have is the sort of the smart constructor for the things containing ciders. Usually validate those. So yeah, we do that.
All right, let's thank Jasper.
Thank you.